Greetings and welcome to episode 36 of the Sustaining the Herd podcast, brought to you by Sechi Agri-Services and Engineering of Raymond, Nebraska. I'm your host, Andrew Wadle, and as usual, joined in the studio with my co-host, Brock Vitek.
Hey there, Andrew.
Hi, Brock. And welcome back to all of our past listeners. We really appreciate you joining us again, and we always appreciate the comments that we get and the feedback that you offer up to us to keep helping us bring to you information in the realm of sustainability in animal ag that really hits the mark and maybe answers some of the questions that folks are asking. And so for our new listeners, we really appreciate you joining us, and we'll just tell you a little bit more about sustaining the herd, at least as what sustainability means to Sechi Agri-Services and Engineering. And really, it means three things, and it can mean a whole lot more probably also, right, Brock, than three things. And so we think of it as first and foremost, and maybe in no particular order, but first as protecting the air and the water. Everybody wants to have clean water to drink and clean air to breathe, and animal agriculture really shouldn't impede upon that. And the second thing is sustainability is doing more with less. It's efficiency and maximizing resources. And lastly, sustainability is business sustainability. We have to have strong agribusinesses in order to continue to function. Businesses need to be successful in order to stay in business. And so as you listen to our episodes, we really try to weave in and out of all those of those three topics, and to, like I said, to try to hit the mark when it comes to sustainability in animal ag. And so just to kind of get started here, some of you may recall, and for our faithful listeners, episode 35, we talked about nutrient management as being the Achilles heel of anaerobic digestion. And we really feel as though maybe, right, Brock, it was a topic that deserved more time than what we gave it.
Mm-hmm. Absolutely.
And so we're going to call this part two because, it's not just about talking about problems. Especially here at Sechi, it's not about the problems. It's about coming up to solutions with problems or challenges. And so that's what we're going to talk about today. We're going to call it part two. And we're going to talk about nutrient management opportunities and solutions for feedlot anaerobic digestion projects. And this applies not just to feedlot anaerobic digestion projects, but to anaerobic digestion projects in general.
That sounds great, Andrew.
So, Brock, you just want to let's just rehash what we did talk about in episode 35.
Yeah, let's touch on a few of the things to get ourselves and our listeners back up to speed here. So the biggest thing, Andrew, was that nutrient management with anaerobic digestion is a completely 180-degree change from business as usual nutrient management for feedlots. And why is that? Well, today, open lot feedlots, I should say, are used to managing their manure in a dry, solid form. They go in, they scrape the pens, there's a stockpile of manure, it gets hauled out with side dumps and spread on fields with manure spreaders. It's a dry, solid product.
And to talk about what dry means.
Yeah. So there's more typically more dry matter than water there, but at the very least it's a stackable product, meaning it can stack in a stockpile and it's not going to flow. It's not a liquid. So anywhere from 30 to maybe up to 80+% total solids or dry matter at times. A dry, solid, stackable product. And feedlots are used to managing the liquid in their lagoons, runoff that's been contained, but that's really low dry matter, or TS, total solids, and typically applied through center pivots onto fields. It's tea water, or looks like coffee. It's not a slurry or a milkshake type of consistency, or at least it's not supposed to be.
And Brock, you can really apply that at irrigation rates, right? Not at nitrogen
Correct.
Or phosphorus limiting rates.
Yeah, still have to pay attention to the nutrients, but by and large can apply that pretty freely. Yep. And so I just described how feedlots manage their manure and their nutrients today. Well, enter anaerobic digestion, where the digestate coming out of the digester is in a liquid or a slurry, probably anywhere from 8 to 10% total solids. And that's coming out. It's too thick, too much solid material in there to go through a center pivot. But it's a liquid. We can't just throw that in a manure spreader or a side dump, then a manure spreader and spread it on our fields. It has to be handled as such. It is a liquid. And not to mention, it can be pretty concentrated in nutrients. So that's really where we left off last time, and I think we can talk about some opportunities and solutions today. But a couple other things I want to mention, just to rehash from last time and remind our listeners that nutrients are a valuable resource, especially for a livestock producer, because they're an agronomic resource. Nutrients are required: nitrogen, phosphorus, potassium, sulfur, zinc, and many others for crop production. Crops need to take up those nutrients to grow and be healthy. And nutrients also have an economic value. They are a form of currency. If you're not using manure nutrients, you're going out and buying commercial fertilizer. That comes at an economic, a monetary cost. So these have value in the marketplace. And finally, nutrients also have what I like to call some social value. Feedlots purchase grain and purchase silage from neighbors in the surrounding area. And nutrients are a bit of a producer's social license to operate in the community or in the neighborhood, oftentimes exchanged or sold to those crop producers in exchange for the grain and the silage. So valuable on many, many levels. And finally, all of these challenges we're talking about here and all these considerations, this stuff can be of project-killing proportion for an anaerobic digester project if it's not addressed up front in the development process. So we need to keep that in mind for the rest of the conversation as well.
Yeah, and just to emphasize one of the points you made, Brock, on the social license. The manure is your social license to exist to some degree. And so just to summarize that, so let's just say you're a feedlot operator and you are selling or giving your manure away to a local crop farmer, and tons per year going away in a side dump trailer, and then you say, well, next season, instead of giving you, call it 50% dry matter material you're going to haul away in your side dump, I'm going to return it to you at 4% total solids in a liquid. That is absolutely a potential game changer. And so, but not a game ender, but a game changer. And so what we need to talk about, just some of the things that we can do to continue to have what the feedlot produced post anaerobic digestion to continue to be the manure product, continue to allow that manure transaction to be the social license to exist.
That's correct, Andrew. And I think a good place to start would be talking about separation technologies. That is liquid solid separation. And I'd like to ask if you could walk into this with us, given that it aligns with a lot of your experience in your career as an agricultural engineer.
Yeah, and so we have this NP and K and solids in the manure stream, and so one of the things that we can do to improve matters is how can we separate out these constituents, the N, the P, and the K, in a proper balance that is conducive to sensible material handling, as well as something that's more tailor-made to agronomic application of the nutrients. And so, any kind of separation in any industry can take on many different levels, more simple to very, very, very complex. And a couple other things just to understand is, how a lot of these nutrients exist. You have a nitrogen in that in the form of ammonia that can be dissolved in the liquids, and then you can have organic nitrogen as well. You can have phosphorus, which tends to be associated with more like the colloidal particles, that is the fine solids, and then the potassium goes along often with the liquids. And so, if you look at the basic, we'll say the Neanderthal version of separation, it would be just solid separation in the form of a screw press or a slope screen or a rotary drum. Here we're separating with an aperture that is maybe a millimeter, and who loves the metric system? Not us. But anyway, we talk about separation with millimeters because, it just so happens you look at your window screen in your house, and your window screen is about 1 millimeter. And so you can kind of visualize that. So when you look at what you capture on, say, a 1 millimeter screen in a separation process, we kind of say it's like capturing the golf balls. It's capturing the really, really big stuff, the undigested feed particles. And then when we go ahead and squeeze that, we squeeze out the liquids. We're left with a very something that really looks like corn silage, but then also is kind of inert. It really doesn't contain a lot of the nutrients. It contains some, but not all that much. And so liquid solid separation in a very, very coarse separation, primary separation, is one step in the right direction and usually precedes everything else.
Yeah, and I might add the solids coming off the screw press would be more of the fibrous cellulosic type of material, just to put that into perspective.
Yeah, it'd be more like a fibrous cellulosic material. Maybe it could be anywhere from 28 to, depending on the machine, but 28 up to maybe 35% dry matter. Again, it sounds a lot like corn silage, right?
Sure.
Because it really is. It's just been through some stomachs.
Mm-hmm. So, Andrew, we go through what you called the Neanderthal primitive separation through the screw press. That's the first stage. From there, we have some different options. We could go one way or maybe a couple others. What are those next options or potential steps after the screw press, if that's kind of the initial phase in most situations?
Yeah, I think what we'll do is go through it in the order of really what we're seeing as being most commercially viable at this moment today. And usually, and what that would be after some kind of a primary liquid solid separation step, you would have potentially a centrifuge. And a centrifuge is where you take this separated slurry and I'm going to greatly oversimplify this, and you basically spin it in a device. And what it does is the centrifugal force forces the solids away from the liquids. And with those solids, you might say, hey, we just separated the solids. Well, usually the primary separation, you might get about 30% of the solids. And again, everything bigger than a millimeter. So everything smaller than a millimeter, which is a fairly substantial portion, is coming on to, say, a centrifuge. And so the centrifuge captures a lot more of the fine solids, and it also captures more phosphorus than primary separation because, as I mentioned, the phosphorus wants to hang out with the colloidal or the really fine particles. And so then we could have a liquid stream that would be lower in phosphorus. But remember that now we've not done anything for nitrogen, because the nitrogen is largely going to stay, at least the inorganic nitrogen, the available nitrogen, is going to reside primarily with the liquids. So centrifuges, they're very commonly used, and they really are a good next step of separation. Where now we're also whereas with the primary separation we produced solids at 35% solids, let's call it 30% solids. The centrifuge, maybe we might produce them at about 28% solids because the centrifuge is capturing finer solids. More liquids tend to be retained with the solids. Just like a finer textured soil would retain more water, a finer textured manure solids will retain more liquids as well. But that's okay, because with those little bit of extra liquids you might retain, you might also pull some nitrogen out as well. Sure.
So a centrifuge sounds like it makes a lot of sense to follow the screw press or the slope screen as some secondary separation. But let's say that we're modeling a centrifuge for our project, and it's just not quite getting getting that effluent, getting that digestate to the nutrient spec that we need it to. There's another technology that we talk about sometimes called dissolved air flotation, or DAF, DAF for short. Where does that come in, and how might that compare to a centrifuge?
Well, basically, it's just the next level. And so, if you can think about solid separation as a Neanderthal first walking and dragging his knuckles along, now the Neanderthal is evolving, and now we're walking more erect and upright. And so, so as we get into the dissolved air flotation and membrane filtration, we're talking about more highly evolved systems that also capture more solids. It just so happens also they are much less prevalent in our animal agriculture applications, and so just a little bit about dissolved air flotation. Really, what happens is air is dissolved, is pressurized into a liquid, and the air is dissolved into the liquid. In this case, manure slurry, and then it's released. The pressure is released, and these microbubbles rise, and the microbubbles attach to colloidal solids. And just like with centrifuge, when you capture the fine solids, you are going to be more inclined to capture your phosphorus. So that's and then basically whatever floats is scraped off the top, and then you're left with a phosphorus, maybe a phosphorus-rich float, and then liquid that still was going to retain most of your nitrogen. And then moving on to the next step, and these aren't looked at as steps always. These are separate operations, and then we have membrane filtration, which is, when you think about any even primary separation, it's a form of filtration, right? Where whether it's a screw press or a slope screen, we're forcing or allowing liquids to pass through an aperture. Whereas with membrane filtration, it's done by pressure. We are literally pumping and pushing a fluid through a really small filter, really small filter. And what happens when you capture more fines, Brock?
When you capture them, you're going to have them build up in that filter. And
then what are you going to capture with the fines? What nutrient?
You're going to capture some more phosphorus and some nitrogen with them.
Yep, exactly. And so membrane filtration is another system for increasing nutrient capture, and it's just pumping across a really fine screen. Again, not like a slope screen where we're just allowing gravity and atmospheric pressure to allow material to go through. Now we are literally using a pump to apply high pressure to push material through. So membrane filtration and dissolved air flotation in industrial applications, they are very commonly used, but just not very much used in animal ag. But they are technologies that have a heartbeat and are widely considered.
Absolutely. And Andrew, I want to help our listeners understand that, like you said, these are typically separate operations. Don't just think of these as all being in series or one step after another. We're always going to have some primary separation, whether that's a screw press or a slope screen, probably more likely a screw press for an anaerobic digester operation if I had to make a guess. And then we'd probably have either a centrifuge or a DAF, correct? And then membrane filtration would come after either one of those, right? So we'd have, say, primary being a screw press, probably secondary, either centrifuge or DAF, centrifuge more common, and then something such as membrane filtration after that, just to give our listeners an idea of the process flow and how many steps are involved here.
Yep, that is correct. And so most of the liquid solid separation, just kind of to summarize this, most of these advanced forms of liquid solid separation are more going to get after your phosphorus than they are your nitrogen. So we still have a nitrogen laden stream. And so what does that really mean? Well, when we're broadcasting dry solids, when we have a lot of ammonia in those dry solids, just the way we're allowed to do our nitrogen accounting, the ammonia when dry manure is broadcast, we assume 100% ammonia loss because of the fact that the ammonia volatilizes. So now, getting right down to it, the challenges with AD is now we have this nitrogen in a liquid form. And at least in the state of Nebraska, if you're applying at rates of more than a half an inch per acre, now you have to account for 80% of your ammonia. So that's a big deal. We went from accounting for zero of it to now we're having to account for 80% of it. And so you multiply that times a lot of tons or a lot of gallons, your N starts adding up really, really fast.
Yeah, the nitrogen balance sheet gets a bit wonky then.
Yeah. Yep, for sure.
Yeah, and so the things we've talked about so far are what I would call mechanical separation. We're physically separating solids from liquids, pulling particles apart in terms of, they're going different directions, physically going different directions. But that doesn't always get us to where we need to be, because you might remember earlier in the conversation, Andrew and I were talking about how runoff water that's contained in a lagoon at a feedlot is applied via center pivot irrigation, and pretty freely for the most part. It's not all that hot of a sample. It's not too high in nitrogen, even though we still need to pay some attention to it. So we need to figure out how we get the liquid digestate, or the liquid portion of the digestate, down to essentially that same spec or standard that a producer's used to in their runoff pond. But right now, as we've followed the nutrients through the separation process, we know there's still a lot of nitrogen in the digestate liquids, a lot of nitrogen. So mechanical separation didn't get the job done here, Andrew. There are some next steps that we can look at that gets more into some chemical and biological transformation and separation of those nutrients to get us to where we need to be. And what are those options?
Well, let's start with maybe what we're seeing done, what's in the field, because I always like to look at what's tried and true, and if not tried and true, what is being done, and at least lurching in the area of being tried and true. And and this might sound familiar to some of our past listeners, but folks may remember when we interviewed Jim Wallace a few well, actually it was many episodes ago now, but they talked about worm farming, of all things, farming, where a dilute manure effluent is applied to beds of wood shavings, and I think it's a bit of a proprietary mix of things, where you put this dilute manure effluent. It's had some pretreatment now. It's probably been treated by a centrifuge, where you take out a large amount of the solids, the suspended solids, and so then the liquid effluent is really sprayed out onto. It's going to sound crazy, but people are doing it. Beds of worms, and it's called vermiculture. You've heard of horticulture? This is vermiculture, and so this manure effluent is put on these beds, and the worms eat it along with what's in the beds, and so you end up having these beds that end up being it's a solid material now, quite laden with the nutrients, and then with a liquid effluent that is very low in nitrogen. So vermiculture, I'd say, as crazy it may sound, it's definitely something worth keeping your eye on, and I believe you'll be seeing more and more of these systems. Does that sound about right with you, Brock? I
completely agree. As out there as it may seem, it's, first of all, it's just kind of cool worm farming to clean up wastewater. That's awesome. And I agree. I think it's becoming more and more prevalent, and it's a solution that really has a heartbeat to help solve these issues that we're talking about. And I think it's a viable option.
Right. And so what this does is, really what this ends up being is there's a lot of nutrients that need to be not disposed of, but just hauled farther in order to utilize really their value. And so we don't want this material to go away, so to speak, because of the fact that it really does have an agronomic value. However, there are systems out there that make it go away. Not an antimatter machine, right, Brock? Because we know those
Not
don't
at
exist. All. But you can have another option would be nitrification, denitrification systems.
Say that 5 times fast, right?
I can't do it. I can't either. So nitrogen denitrification means, well, someone might say, well, why can't we just get rid of this nitrogen into the air in the form of ammonia? Well, that's not a good thing to do necessarily. And so
that doesn't help with clean air and water.
Doesn't help with clean air and water. However, chemistry would suggest that, and chemistry proves out that we can get rid of nitrogen in a form that's not harmful, so it's not a pollutant. And because after all, Brock, what's the most common constituent in the air that we breathe?
Nitrogen, atmospheric nitrogen, N2 is the chemical formula.
So there are systems called, and now we're into the realm of more industrial treatment processes. And hey, listen, this is a complicated problem, and so it requires complicated solutions. And this is more of a complicated solution where, just with a series, maybe I'll just oversimplify this a bit, but a system of aerating on and off a slurry. What we can do is, when you time this aeration process in a manner that instead of releasing ammonia, you satisfy the consortium of bacteria so that they evolve nitrogen gas, N2. It's all over in the environment. Is, like I said, it's the most prevalent gas that you breathe in air, and so we can actually drive off ammonia as not a pollutant, but we can drive off the ammonia so that we have less ammonia to have to apply through our pivots, should that be our goal.
Mm-hmm. Yeah, in fact, 78% of the Earth's atmosphere is nitrogen, N2. So we're just creating that and putting that in the air. Really, no negative environmental impacts at all. And this is another biological process, as Andrew said. Bacteria, microbes are doing the work to convert that nitrogen into the form of N2. But there's something I'd like to note here, and that is, This does take those, even though it's not an antimatter machine, it takes those nutrients and essentially gets rid of them into the air, puts them into a form that is not usable for us for crop production. So that is a trade-off with this one, is we are essentially eliminating or reducing the amount of nitrogen that's available for fertilizer usage. Even though it does take care of one problem, that is something to be aware of with this one.
Yep, that's spot on. That's spot on, Brock. That is what it is. So it might not be quite so preferred because you're not getting the agronomic value of the nitrogen.
Mm-hmm.
And so the next one I just wanted to talk about is, again, it's another very, very common industrial process, and that is ammonia stripping. And as I said, there are ways that you can, particularly by heating manure and blowing air through it. Roughly speaking, it is possible to volatilize manure or volatilize ammonia into the atmosphere. But we don't want to do that. We don't want to do that for a variety of reasons. One, it's a waste, and B, because it's potentially a pollutant. So, but nevertheless, a very common industrial process is called air stripping. And so in air strippers, what happens is the manure is heated and air is passed through it, and it basically liberates the ammonia, but it's also mixed with sulfuric acid, rather. And the combination of the ammonia with the sulfuric acid produces ammonium sulfate. And ammonium sulfate is really a commercial fertilizer.
Yeah, a very valuable commercial fertilizer product, in fact.
Yeah, a very, very concentrated, valuable commercial fertilizer. So now, instead of having our nitrogen spread out over millions and millions and millions of gallons of water, we're really concentrating the nitrogen into a form that is, on par with being a commercial fertilizer, something that can be monetized and can potentially be hauled far distances.
That's right. That's exactly right. I think you did a great job laying all of these solutions, potential solutions out, Andrew. And I would like to hit on another point with these, and that is the magnitude of the CapEx, or the capital expense of these further treatment options. They certainly come at a cost, but a project does reach a point where, this can be a deal breaker, a project killer if we can't get this nutrient management figured out. So sometimes it's necessary to have that extra spend, but I want our listeners to be aware of that. The mechanical liquid solid separation, that certainly comes at a cost, but it's not usually a deal breaker. But these further treatment options, they can get pretty expensive in a hurry, and just want you to keep that in mind. Even though they can accomplish what you need to do, they certainly come at a cost. You have to ask yourself, is the juice worth the squeeze here?
Yeah, and the more complex the system becomes, the higher the chance that you are not going to operate that system yourselves. And usually that's probably not too terribly surprising, because most of the anaerobic digesters that are operating successfully, they all have contract operators, because usually, whether it's dairymen or feedlot operators, they already have a day job and they don't have the time to manage an anaerobic digester plant. And so as these systems get more complicated, digestion right on through nutrient separation, you have the higher and higher chance, because of the complexity, in addition to the CapEx that you're going to have, it comes along with an OpEx that's going to potentially include an operator. But as those systems get more complex, we talked about, like with nitrogen stripping, you have an output. You have potentially a monetizable output that goes and offsets some of that OpEx, or offsets the OpEx.
That's exactly right, Andrew. I agree. So I think we've covered about everything here, at least most of the opportunities and solutions that we're seeing in our day-to-day work these days. So I'd like to round out the episode by just hitting on a few take-home points or lessons for developers and anyone else who might be listening, similar to what we did last time. And the first one is that, as I think you've probably seen in the episode here today, there are several solutions out there that exist today. They're tried, they're true, they're operating in some form or another today, that are able to get nutrients into a manageable form and quantity to meet the specs needed for your project. But they do come at a cost. But they are out there, and that's what's important. And also, we know from experience that nutrient management is easier and much less stressful to figure out on the front end of a project very early on, or as early on as possible in the development process. Do not wait until the project is signed, sealed, delivered, and ready to build the thing before you start to think about this. Figure it out early on, because it might make you might find out that, hey, this is a project killer, or it's a project killer today, maybe not next year, but that's okay. Figure that out early on and save everyone some headache and heartache and dollars potentially.
That's right.
And finally, I said this one in our last episode, and I'll say it again because it rings just as true today as it did a couple of weeks ago. Engage the right team early on. Your livestock producer partner on a project, agronomists, engineers, decision makers, stakeholders, you name it. Anyone who might be affected by this and or has something to bring to the table, get them engaged early on to figure out the best solution possible for nutrient management on your project. Make sure all those bases are covered.
Yeah, and it's when we talk about anaerobic digesters, we shouldn't just say an anaerobic digester. It's an anaerobic digestion system, and that and in engineering we always talk about how drawing the boundaries around the system, and in an anaerobic digestion system, the boundaries are the person scraping the pens, we're talking about in feedlots now, from the person scraping the pens all the way out to the most remote field that's receiving manure. Those are the boundaries of the system. And so all those things need to be considered.
That's right. And one other thing I'd like to add, Andrew, when we were first stepping into talking about some of the further biological treatment options, you'd said something that really hit home for me. And that was that, these things like NDN and ammonia stripping, worm farming get more into the like industrial type of treatment, something you might see at a slaughterhouse or maybe a municipal wastewater treatment plant for a community. And I'd like to remind all of our listeners, I think developers know this, but just for everyone, an anaerobic digestion project, it really is, it's a renewable energy production facility. It's an industrial facility in many ways. And these digestate treatment systems are more on the industrial scale and front as well. So just keep that in mind. These are complex projects and complex systems, as Andrew said, and they need to be treated as such. Yep. So that's my last point I'd like to make here today.
Yeah. Well done, Brock.
And with that, would like to say thank you to all of our listeners, both new and returning, who are choosing to join us for this episode today. And we look back to being with you again in a couple of weeks. Until then, thanks for joining the herd today.